Welcome back. So in our last video, we gave a very quick critique of some of the potential issues that occur in likelihood statistics and kind of alluded to how Bayes would allow us to um, address those critiques, and the crux of that kind of centered around this idea of could we get what we really want out of statistics, the probability of our models and our parameters given our data, and how do we get there? And to get there, I'm going to need to set up a few basic rules of probability that we haven't really dove much into this semester yet. So these are the ideas of joint, conditional, and marginal probability. So imagine this is set X, this is set Y. These pluses are helping us visualize probability. There's 10 of them, so each of them represents 10%. And so we might ask about, for example, what's the probability, the joint probability of X and Y? So X and Y occur together 3 out of 10 cases. So we would have a joint probability of X and Y, in this case of 30%. So joint probabilities, allow us to ask about the probabilities of multiple things occurring. Conditional probabilities, on the other hand, allow us to ask about the probability of one thing occurring given that something else occurred. So we might ask, what's the probability that we are in set X given that we already know we're in set Y? So if we condition on set Y, there's 3 observations there out of 6 total. So the probability that we're in X, given that we know we're in Y, is now 0.5, 50%. There's a 50-50 chance we're in X if we know that we're also in Y. And then we might also ask about what's known as the marginal probability, just the probability that we're in X, say. In this case, there's 7 pluses representing 70% chance that we are in X. Should also note that the marginal probability can be reached essentially by integrating or summing over the different joint probabilities. And the name marginal probability kind of comes from the fact that we often think about this as being the margins of a contingency table. So if we wrote down what we're seeing up here in terms of a contingency table, we might say, what's the probability of being X and Y? Well, that's 0.3. What's the probability of being in X that you're not in Y? Well, that's 0.4. And the probability of being in X is just the sum over the cases of Y. In this case, we only have, X given Y and X given not Y. But if we thought of Y as a whole continuum, well, if it was discrete, we would sum over all the different possible cases of Y. And if it was continuous, we would integrate over those possible cases of Y. So our marginal probability, the probability of X integrating out the possible values Y could take on. Cool. So it turns out that these things, conditional, joint, and marginal probability, are related to each other. So this here just rewrites what I had at the bottom of the screen before. And it turns out that the conditional probability, the probability that we're in X, given that we know that we're in Y, is just the joint probability divided by the marginal. So for example, if I want to know the probability that I'm in X, given that I'm in Y, I would look at the column Y, so I know I'm in Y, and I would say the probability of that, 0.3, divided by the total marginal probability, 0.6. And so I would say that there's, again, a 50-50 chance, 0.5, which I got by taking the probability of being in X given Y divided by the probability of Y. If I multiply both sides by the probability of Y, I get this simple representation that the joint probability is the conditional times the marginal. And if I integrate both sides, I can see that the probability of x and y, again, that's just the marginal probability of x, can also be written as the integral of the probability of x given y, probability of y. Again, because the joint is just the conditional times the marginal. And that these two relationships will come in handy in a second. Okay, so as I said on the last slide, we have this relationship between joint, conditional, and marginal, where the joint probability distribution is just the conditional distribution times the marginal. So if I want to know the probability of x and y, I could calculate that as the probability of x conditional on y having, or in this case, theta. If I want to know the probability of x and theta, I can think about the probability of x conditional on theta, and then multiply that by the probability that theta occurred. I can also write down this relationship in the other direction. So I can write down the probability of theta and x is the probability of theta given x times the probability of x. So it's just the same thing written in the other direction. Now you can do a simple equality here, which is the probability of x and theta and the probability of theta and x are really the same thing, because they're, it's an and case. And so when you have the probability of x and y or x and theta, it doesn't matter which order you're talking about. And so I can say from there, the probability of theta given x times the probability of x is going to be equal to the probability of x given theta times the probability of theta. Now, if you hold on with me for just one more second, what I'm going to do now is divide all of this by the probability of x to get this equation right here. The probability of theta given x equals the probability x given theta, probability of theta divided by the probability of x. Now that equation right here is known as Bayes' theorem. And Bayes' theorem is the basis for all Bayesian inference and all Bayesian statistics. And Bayes' theorem is in no way controversial. You saw the derivation yourself. It's pretty straightforward. But what's important is what we're going to see later is some of the implications of this theorem. I also want to point out that there's some key important names for the parts of Bayes' theorem. First, here, the probability of x given theta, we've seen this before. This is just our likelihood. This here over here on the left, the posterior, the probability of theta given x, remember, that's what we said we wanted. So now we're talking about the probability of the model given the data. And what Bayes' theorem does is it gives us a way of relating the probability of the data given the model from our likelihood to the probability of the model given the data, which is what we want. So that's kind of the beauty of Bayesian inference and why it then allows us to do some pretty powerful things inferentially. And that said, at the heart of Bayesian statistics is still the likelihood. So even if you're a Bayesian, the likelihood never goes away. We still always need to be able to write down something about the probability of our data given our model and its parameters. But the thing is, to get to the posterior, we need this thing over here called a prior. And the prior represents that information that we had before the experiment. Remember when in the last lecture, we talked about, one of the limitations of frequentist statistics is we don't have any way of using our prior knowledge before we do inference. So we can't say, is this particularly plausible? Is this particularly unplausible? What is the weight of the evidence that I already had in hand? And the prior allows us to do that. It allows us to say, what did we know about this system before we got this particular new set of data? And it's called the prior, is particularly because it represents our understanding of theta before we see the data x. The other thing here in the denominator, this probability of x, I'm going to quickly do a quick substitution and say Well, the probability of x is a marginal that I can get by integrating the probability of x and theta, which is, again, it's just the integral of probability x given theta, the probability of theta. That seems like a very unhelpful substitution initially. Why, if I have the probability of x, why would I replace it with an integral involving a conditional and a marginal? The reason is when I write this out in this form, which again emphasizes what we're getting out of this is the probability of the model given the data, that this thing in the denominator is actually just the integral of the thing that's in the numerator. And so what this thing in the denominator represents is just a normalizing constant. So remember, when we talked about probabilities, we made the point that whenever you have a probability distribution, the probabilities have to sum to 1. And so when we take the likelihood and multiply it by the prior, there's no guarantee that that by itself is going to sum to 1. And so what we do is Bayes' theorem says there has to be this normalizing constant in the denominator that ensures that your probabilities are correct, that they sum or integrate to 1. So again, we have what we want to get out of this, the probability of our model given our data coming from our likelihood, probability of data given our model, and our prior. And I should also note that Bayes has this wonderful iterative nature where the posterior from one analysis, the probability of data, the probability of the model given the data from one analysis can be used as the prior for the next analysis. So I can take, if you want to know where this prior comes from, well, it often, can come from a previous posterior. So you can say, what did I get last time? I'm going to update that with new information. So that kind of wraps up the derivation of Bayes' theorem. In the next video, I'm going to talk about kind of how we apply this.